All right, let's get started. So, here's the setup. We have airflow. We have this left side, which we're going to denote as 1. We have this right side, which we're going to denote as 2. Diameter on the left of the tube is half that of the one on the right. The velocity on the left is 30 meters per second. But we're looking for the change in height of these two pistons once the air is cut off. So let's start with Bernoulli's, because we're working with laminar flow here. Bernoulli's says pressure plus 1/2 density times velocity squared plus density gravity constant times height is equal to, not 0, I meant constant, sorry. You can call it C. So, if it's a constant, then the left should equal the right, which means pressure on the left plus 1/2 the density of the material we're working with, which is air, velocity on the left squared plus density of air, gravity times height is equal to pressure on the right plus 1/2 density of air, velocity on the right squared plus density of air times gravity times height. So we have this. What does that tell us? First, we can look at the fact that plus rho GH and plus rho GH appear on both sides. So we can just drop that. Now let's isolate the pressure values. So we get P2 minus P1 is equal to 1/2 density of air. And we're going to divide that out because it appears on both sides. V1 squared minus V2 squared. Okay, great. So we don't know what this is. We do know what the density of air is, and we do know what V1 is. But this detail here, the diameter detail, tells us everything we need to know about V2. So given that the diameter of the circle, that's a really bad circle, ignore that, is twice that of the one on the left. That means the area on the right is 2 squared that of the one on the left, which means we have the ratio A2 is equal to 4A1. What does that tell you? Well, we know that A1 V1 is equal to A2 V2. Now let's just fill in the blanks here. Let's isolate V2, which is what we're looking for. So we get A1 over A2 over V1. That becomes A1 over 4A1 times V1, which is equal to, because we can cancel out that A1 term, 1/4 V1, which is 30, and that gives us 7.5 meters per second, right? Great. Now we have every term that we need to find the change in pressure. So, let's fill in the blanks here. Change in pressure, delta P, is equal to 1/2 density of air, which is 1.2 kilograms per meters cubed, times V1 squared, which is 30 meters per second squared, minus V2 squared, which we just found to be 7.5 meters per second squared. That gives us 506.25 as our difference in pressure. Okay. Great, so now let's consider the situation we're working with. This tells us is that the difference in pressure between the right and the left is 506.25, which means the pressure here is 506.25 greater than here. So what happens when we turn off the air? Well, incremental difference in pressure can be written as density times gravity times height. So then if we integrate it, we get change in pressure is equal to density times gravity times height, or change in height, excuse me, because that's the only one that's not constant, plus the integrating constant. We just found change in pressure to be 506.25. The water is the density of water is 1,000 kilograms per meters cubed. Gravity constant is 9.81 meters per second squared. But when the air is turned off, there's no difference in pressure, right? Which means that there's no change in height, which means that delta H is just 0. So now we're left with this whole thing is gone, that's just 0. So our constant that we're going to be working with is just 506.25, which is what we just found. Let's put it all together. Let's bring back Bernoulli's. We're looking at the water now, and then the water has. I'm working with the delta P, so delta P is not equal to, it's plus 1/2 density of water times velocity of the water squared plus density of water times gravity constant times delta H, which is what we're looking for, is equal to C. Let's start filling in some blanks. We know that there is no change in pressure because the air's been turned off, so that's a big old 0. Plus 1/2 density of water is 1,000 kilograms per meters cubed. But the velocity, because it's not moving, is just 0 meters per second squared. Plus 1,000 kilograms per meters cubed. It's gravity constant, 9.81 meters per second squared. Times delta H is equal to the constant, which we calculated to be 506.25. We bring all this down, so we get 9,810 times delta H is equal to 506.25. That leaves us with a delta H of 0.0516 meters, which we can convert by multiplying by 100 to 5.16 centimeters. So our delta H is 5.16 centimeters, but what does that mean geometrically? Well, recall, initially when we calculated out for change in pressure, we used P2, this side, minus P1, this side. So if we have a change in height of 5.16 centimeters, that means the right side was higher than the left side by 5.16 centimeters.